Hello class. In the last video, we learned a way to solve one special type of first order equations. That was separable equations. In this video, we're going to look at a different type of special case, which is linear equations. And we learned about linear equations in chapter 1. And so I have written here the basic form of a linear first order equation. So we're still only worrying about first order. So let's kind of do a little bit of a review and see why this is a linear first order equation. So first of all, here are the things that have y's in it. It has only one derivative, so this is why it's a first order. It's got one derivative of y and then just a y by itself. And then each of the y terms have what's called a coefficient that have only x's in it. Okay, so these are coefficients, and that's all the y pieces are that. And they only have x's. It doesn't matter what those look like. They can be anything any combination of x's or constants or whatever, but just no other y's. And this is linear if you think back to, first year algebra in high school or whatever. Linear equations, they look like y equals mx plus b, but another way you could write it would be like ax plus by equals c, where you had constants. So this is a line. And your variables here were x and y. So that's similar to the variables that we have in our differential equation, which were y and dy dx. And the coefficients are these constants a, b, and c. So the thing that makes this thing linear is that you don't have things like, you don't have things like y squared or xy e to the x, e to the x, etc. And so it's the same thing with the differential equations where you don't have your variables, y and dy dx, doing all sorts of crazy stuff. Okay, so let's go back to our differential equation. So I have said a couple times in the past that linear usually is easier than nonlinear. So let's take a look at this and think about if we already know how to solve this or in which cases. So let's think about some special cases. One. Let's suppose a naught, so that's the coefficient in front of y. Let's suppose that's 0. Okay. Then, so that's if a naught equals 0, then we have this equation. Just the a naught term, a0 term goes away, so we have a1 of x dy dx equals b of x. And in this case, you can see that this is actually a separable equation. So now this is separable. We can just divide the a1 over and then integrate. Divide by a1 and then integrate. So we know how to solve this case, so that's great. So now let's think about another special case. So if, let's suppose that a1, so a1 is our term in front of our first derivative. That's, why we decided to notate it that way. So if a1 prime of x, if it happens that one coefficient, if its derivative is equal to the 0th derivative, or the 0th coefficient, what does that mean? Then we will have a1 of x times y prime plus a naught of x times y. Okay, this was the equation that we were given in the first place, the left-hand side of it. And we can rewrite this as a1 of x, y prime, and we can replace the a naught by a1 prime of x times y. And then we can rewrite this like this, d dx, the derivative of the product a1 of x times y. And why is that? That's because of product rule. So this is sort of a tricky observation, but explains why we would think about this special case, even though it doesn't really why would you think that you want to consider this sort of special case? And the reason is that if you have the special case, then you can use product rule to write this thing really nicely. So then our equation L, so the equation L from before becomes, let's go back to black. The left-hand side looks like d dx of a1 of x, y equals b of x. That was our right-hand side. And then we can just integrate. So then a1 of x, y equals the integral of b of x dx plus c. And then we have a solution. We have our y, what we're looking for, equals 1 over a1 of x times the integral b of x dx plus c. So in both of these special cases, in particular in this special case, we can solve the equation, and that's great. Okay, we've got a solution. But as you can see, that's sort of a weird special case. So the trick that we're going to use here is to try, if we're given an arbitrary linear equation, can we try to make it fall into case 2? And that's the trick that we're going to see now that's going to enable us to solve linear equations. So now what I'm going to do is I'm going to take my arbitrary linear equation from equation L, and I'm going to rewrite it into standard form, which looks like dy dx. We want to get the dy dx by itself. So dy dx plus some new coefficient p of x times y equals another new coefficient. And those coefficients just come from dividing off by the a1 of x. So this equals, p of x equals a naught of x divided by a1 of x. And q of x equals b of x, what we had on the right-hand side, divided by a1 of x. And there's really no difference between what we had before in L and this version now. It's just sort of shuffling things around. It's like the difference between when you're talking about linear equations in just a regular algebra class, the difference between ax plus by equals c and y equals mx plus b. Sometimes it's easier if you have that y by itself so that you can see sort of the shape of everything else. So in this case, we have the dy dx by itself. So what we want to do, our guess is that we can sort of multiply this whole equation by something that's going to put it into the case 2 that we had earlier. And so what would that look like? So in other words, can we find, we're going to call it mu, some function mu of x such that, now if we multiply through, our new equation will look like mu of x dy dx plus mu p of x y equals mu q, such that this falls into case 2 from the sort of previous screen. So what we would need to have there is that, remember, let's run back and see it. We had the coefficient in front of the first derivative, its derivative equals the coefficient in front of y. So we would need to have mu prime of x equals mu of x times p of x. So now the question becomes, can we find a mu of x that satisfies this equation that I just wrote out here? Well, I mean, think about this equation now. This is a differential equation, right? It's got mu prime of x equals some other function of x. It doesn't have any y's in it, so now it's a differential equation in x. But it's a really simple differential equation, and we should be able to solve this just by integrating. So let's write it out a little bit differently in the notation that we're a little bit more used to seeing differential equations in. So now we've got d mu dx equals mu p, and I can divide off, and this is separable, right? So I can get d mu divided by mu equals p dx. So actually, let me rewrite this left-hand side so it's a little bit more clear. I've got 1 over mu d mu equals p dx. And now I can just integrate it. Well, we can integrate the left-hand side. That's easy enough. That's just an ln of mu. We'll put a of x there for clarity. And depending on what p is, hopefully we can do that. We can integrate that. So we'll just sort of write it like that. And now if we want to solve for mu of x, we just have to take the exponential of both sides. So mu of x equals e to the integral of p of x dx. The right-hand side looks kind of gross, but you know, once you actually know what p of x is, because that's a given to you, that's something that you can hopefully calculate. And so notice that I didn't put a constant of integration in here. So the reason that I didn't write a constant in there is that I'm not trying to look for any mu that satisfies this equation. I just need one that is going to work for my equation. And so I'll just take it with the constant equals 0 for simplicity. So what we have now is we've defined this mu, and this is called our integrating factor. So let's go back to the equation that we wanted to solve in the first place. And we have it in our standard form. And so what we're going to do next is we're going to multiply by mu of x. I mean, you know from, right, your very first algebra classes that you can multiply through an equation by something and it's not going to like change the solutions. So possibly in some very trivial cases, but we're not going to worry about that. So we've got mu of x dy dx plus mu of x p of x y equals mu of x q of x. Now, because of the way that we defined mu of x as satisfying this equation, we can replace mu of x p of x with mu prime of x. So we can replace mu times p with mu prime. And then our equation becomes mu of x dy dx plus mu prime of x y equals mu of x cubed x. And now, just like we did before, we can use product rule. And we get the derivative with respect to x of the quantity mu of x y equals, let's see, on the right-hand side, we've got mu of x q of x. And then I can just solve this straight out. So we integrate and divide by mu, and we end up with a solution, which is y of x equals, so first we integrate the right hand side, so we get the integral of mu of x q of x dx plus a constant, and then that whole quantity is divided by mu of x. And look at this, we have a solution for our differential equation. And it's an explicit solution that is written out exactly y of x equals blah, 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 blah. And it gives you a formula based on the q that is given to you in the problem, and then the mu, which is given to you by this formula right here. So if you know this formula for mu, then you can, and you know q from the problem, then you can plug it right in and you have your explicit solution. So in summary, you could sort of memorize this formula, but it's a little bit long. The easier formula to memorize is what mu is, and then just remember that you have to multiply through and then use product rule to rewrite it, and then you can just solve the equation like we just did. But I mean, either way. Let's do an example now. So let's take an equation 1 over x times dy dx minus 2y over x squared equals x cosine x for positive x. So this is a linear equation. We'll put it in standard form. So let's see, put in standard form. And we'll maybe see things a little bit clearer how they look. So if we have dy dx and we multiply through by x, then we get dy dx minus 2 over x times y. And we've multiplied through by x, so on the right hand side we get an x squared cosine x. And so in the notation we were using before, this is p of x, and our right hand side is q of x. So with this point, we want to find the integrating factor. And that is mu of x. And remember, that's this equation right here. So e to the integral of p of x. E to the integral of negative 2 over x dx. Well, that's easy enough. So we have e to the negative 2 ln of x. And I'm going to do this really slowly for those of you who are still a bit freaked out by exponentials. It's understandable. So this is like e to the ln of x to the negative 2. And that just gives you x. So this whole thing is x to the negative 2. So with a lot of these problems in the homework and stuff like that, usually the integrating factor simplifies down to something that's actually like sort of easy to work with, which is nice. So now we'll go back to our equation. Now that we have our integrating factor, what I'm going to do is multiply by mu of x. So our equation in black, we have x to the negative 2 dy dx minus 2x to the negative 3 y equals cosine of x. So those x squareds cancel on the right-hand side. Next, we will rewrite the left-hand side with product rule. And we know that the left-hand side is going to look like d dx of x to the negative 2 y. And then the right-hand side is still cosine x. And now we can integrate and solve for y. And we get x to the negative 2y equals the integral of cosine of x plus a constant, which of course we can do. So what is that? Sine of x plus c. And then we finally get y of x, the thing we're looking for, we'll multiply over by x squared, and we get x squared sine x plus constant times x squared. Okay, it's important that that x squared multiplies through both to the sine x and to the constant. And so anyway, this is our solution. Draw that box a little bit better. There we go. All right, so that's an example of how we solve linear equations. And what's really interesting, if you think about what we just did, is that we started with sort of the arbitrary case for a linear equation, and we worked through how it, no matter what, you can find this this integrating factor and find a solution. So this actually gives us a nice theorem, which is along the lines of when we saw earlier. So I'm going to write this out. So we have an existence theorem, just like we saw before, but this actually has some other nice properties. So what this theorem says is that if you have an initial value problem, basically the thing that we've been considering, a first order linear equation, as long as you can do all the steps that we did in this class, or in this video, where we were able to integrate and blah, 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 then you can find a solution in the same way that we did. And so those conditions really means that P of x and Q of x have to be continuous. That's enough to guarantee that you can take our antiderivatives and those things like that. And so if your P and Q of x are nice enough, which in this case is not terribly restrictive, then you can get a solution. And what we talked about when we saw our previous existence theorem was that it didn't tell you anything about how to find that solution. But this proof, I'm not going to go through the proof because we essentially already proved it. This proof not only told you that a solution exists, it told you exactly how to find it. It gave you the formula for it. So this is actually a very strong theorem, and a good example of why linear equations can actually be pretty nice. You can actually find a solution and you know exactly how to do it. So in the homework and on exams and whatnot, you will sometimes see problems that may be both separable and linear. And so now you have, in those cases, you have two different methods for solving it. You can solve it using the approach from section 2.2 or the approach that we've just seen. And unless the problem specifies that you should use one way or another, it doesn't matter how you get to the solution. You hopefully, if you're doing it right, will get the same answer either way. So That's it for this section. In the next video, we will see one more special case of first order equations that we have a method to solve.